Is it quantitatively accurate?
Qualitatively, I mean, there's, this isn't tricky, and there's only two ways you could answer this and be anywhere close to being right.
And it uses all three of them?
Yep. One, yeah, and each one only once. So think about vector addition, right? When we add something with tails and tips. When you add two vectors, you put
the tail to the tip.
Mm-hmm. Mm-hmm.
Oh, so
and so
it couldn't be B and C together.
Right, yeah. So you couldn't do B plus C with this. That's not what this means
So
here.
To be A plus C plus B.
A plus C equals B. Or you could have gone C plus A equals B, but then again, that's kind of going in the wrong direction. Although you would be right, I mean, technically, I think. Like if you reversed all the arrows, then you'd have A or C plus A goes to B. But here, right, this is what this is. Yeah? Everybody buy that? Like, for instance, if I just drew those two vectors, right? Like, think about if we just had two vectors, A and C. Here's A. Here's C. It looks like that. We'd say, well, how do you add two vectors? What would the resultant be? Well, you would take the C and drag him up here and draw him like this, right? And then the thing that you would end up with would be going from the first tail to the last tip. And that would be your B, right there. Right? Now, here's something. We didn't define this, but we did talk about this. That we defined vector addition, but we didn't define vector subtraction. But it should be obvious what vector subtraction is. So like, if we have some vector u, and then we add a negative vector v to it, right? That's what we mean by vector subtraction, right? So u minus v, like that. And so, like, component-wise, this is what we got. u1, u2, minus, or plus a negative v. Negative would be negative v1, negative v2, right? Because a negative vector just means multiply everything through by a negative, right? So that's what this is. And so, really, you're just taking the first ones, u1 minus v1, u2 minus v2, and that's the vector that we call u minus v. And we could treat that as one vector, right? Because obviously, you add two vectors together, you get a new vector. Ditto here, you've just added two vectors together, and so you get a new vector. That's the new vector. Those are the components of it. And so we could write it like this as one vector if we want, whatever, it doesn't matter. That's not really the point of what I'm getting at. The point is, now here's another point. What happens if I subtract a vector from itself? What do you think I get?
0.
What kind of 0?
Oh, 0 vector.
The 0 vector. Exactly. So let's look at that, right? u1, comma, u2, minus, which is just plus negative u1, u2. That's the same thing as u1 minus u1, u2 minus u2 equals the 0 vector, 0, comma, 0. Yeah?
Yeah.
Are you, what's going on with you?
Looking for a pencil.
Then say
I think
something.
I have.
He's like, come on. Now you're like, well, I guess you're not that far behind because this stuff, I mean, really, you don't need to write it down. But come on. You just throw a pencil. You guys, man, I swear. Okay. So, now here's another thing. One more thing, since we're taking our time. If we have, and you've proved this before. Any vector plus the 0 vector is equal to what?
Any vector.
Whatever that original vector was. So u plus the 0 vector is equal to u. Okay? Okay. So this is just stuff, I mean, we really didn't even need to say it. Vector subtraction is defined by saying just plus the negative of whatever you're subtracting. If you subtract a vector from itself, you get the 0 vector. Okay? Okay, so here's this. Now watch what we're going to do. This is where you need to pay attention and start writing stuff down. You ready?
Yeah.
Okay, here we go. So, let's get C by itself. C is equal to what?
B minus A minus B.
Is equal to what?
B minus A.
B minus A.
Or, yeah.
Right?
Or
And
negative A.
in this case, right, like, this works just like addition and subtraction, right? So, like, in other words, what I've just done is I've subtracted A from both sides here. And really, we're jumping a step, because the step that I jumped was I subtracted A from this side. I subtract A from this side. I have A minus A plus C. But A minus A is the what vector?
Zero vector.
The zero vector plus anything is equal to?
C vector.
That's just C by itself, right? So it still works, right? But the thing is, we didn't know that about vectors. Vectors might not behave the way regular numbers do. But it is true in this case that they do behave in this way, and so you can just subtract a vector from one side of the equation and it ends up on the other side of the equation. That's cool. There are certain times where things that you think, like from regular arithmetic, are going to work and don't. So like for instance with matrices, if you multiply two matrices together, A times B, that is not the same thing in general as B times A. Yeah, it's not necessary. Some certain special matrices have this property, but in general, just a regular old matrix, not going to have this property. So you have to be careful when you're dealing with, you might think, oh yeah, if I subtract A, it just ends up over there. Maybe, maybe not. It turns out with vectors, yes, that's how vectors work. And so we're good. And so we could say then, and this is the whole point, this vector right here, C, we could write this as the vector B minus A. So here's the vector, B minus A. And we're considering that as one vector. Now what did we just say, that A plus C equals B?
Yeah.
Let's check that. Let's see. Does A plus, so we have the vector A plus the vector B minus A, is that indeed equal to B? Well, yeah, and like in this case, your intuition from regular old addition and subtraction of numbers does work, because you've already proved that the vector A plus B is the same thing as B plus A. So we could rewrite, and so I guess we could write it like this. B plus A, same thing, minus A. We've already proved that that is the zero vector, and the zero vector plus anything is just whatever it is. So yeah, indeed, it works. It works. We could write this vector as a difference of vectors. That will be important in a minute. Just wanted to get through that. Any questions on that? Pretty simple stuff. But again, when it comes to vectors, we have to verify. When it comes to any new mathematical object, we have to verify that it behaves the way that we think it should, because sometimes it will not. And that was the thing on the homework that I've written on your stuff, is you kind of, in the cases that you guys did, you just kind of assumed the property that you're trying, because you're so used to saying, oh yeah, if I have a number, it distributes over addition. You have to show that in the case of vectors. It turns out to be true, but we have to show it. So, okay. Now, another thing we could have done here, how would this have changed? Really, and let's do this. Let's say that my original picture that I put up on the board, I'm still asking you with A, B, and C, we want to fill in the blanks, but now, let's say that that's what I drew. Now, how should that equation read?
B plus C equals A.
B plus C equals A. And now let's get C by itself. We get C equals A minus B. And so this vector now is no longer B minus A. It's A minus B. And what happens when you multiply a vector by -1? What does it do geometrically to the vector?
Flips.
It flips it. And sure enough, right? This was our original vector when it was going in the opposite direction. And what happens if you multiply that by -1? Well, now we prove that this distributes over, and so you get negative b plus a, and we prove that vectors, that you could add them in opposite orders, and so, hey, what do you know, right? You take that vector, multiply it by a -1, and it does indeed flip the orientation. That's cool. Are those two vectors, a minus b, and our original b minus a, are they the same length?
Yeah.
It did not change, did it? And obviously, if you multiply something by -1, it should not change the length. It should change the orientation, but it should not change the length. So that's going to come into play a little bit later. I just want to have that stuff down, and we're going to actually use that today. It's not just an interesting thing about vectors. So just one more time, homework, I just want to say it. Homework 24. On page 606, there's a pink box, and you are to prove all of them. There's numbers 1 through 5. I will write it on the board today, and we might prove one, maybe. But you will do these. Now, 614, numbers 1 through 23 odd, and prove number 40. Number 40. Okay, so here we go. Today, we are learning about the dot product. So product. We've learned how to add vectors. We've learned how to subtract vectors. We've learned how to multiply vectors by a scalar. Let me just ask this. A scalar is, well, we talked about this. A scalar is something from a mathematical group that or mathematical set I've called a
Field.
Good, right? Okay, so there's, for every and the entries in the vector are in some field. In our class, we are doing real numbers. So whenever you see a vector, and in our class, we're only doing two-dimensional vectors in R2. So that's a real number, and that's a real number. So we're on the plane. But everything I'm about to say generalizes to any field and any dimension. It doesn't matter how many entries you have in your vectors. Everything I'm about to talk about works for anything. This is, yeah. Okay, ready? So, given two vectors, the dot product of A and B, written A dot B.
So not times though?
Not times. Because we don't have, it's not vector you could think about it as a type of multiplication, but it's called dot. A dot B. A dot B is defined as A1 times B1 plus A2 times B2. That is what the dot product is. This is also called the scalar product. It's also called the inner product. Now, the thing is, there are lots of different types of inner products. This is one type of inner product. The dot product is a specific kind of inner product. And I said that there are inner products and there are also outer products, which you will not talk about for a long time. But notice something. We've taken two vectors. What sort of thing is this? Is it a vector? No. What sort of thing? And in our class, I said that these are always what types of numbers?
Real number.
Real numbers. That's a real number, and that's a real number, and therefore A times B is a?
Real numbers. It's just
that's a real number, that's a real number, and so that times that is a?
Real.
And when you add two real numbers together, you get a? Real number. So the thing is, and this is why it's called a scalar product, because you take the product of two vectors and you get out a scalar. And it happens to be a scalar of the same sort of field that your vectors exist in. Now check this out. Every function that we've messed with so far, every function that we've ever talked about, except for briefly, but every function that we've ever talked about is a map, which maps inputs from the real numbers into outputs from real numbers. This is just a fancy, and so like if I had some function, let's say f of x equals x squared over 1 minus x, something like that. I would say this is a map. What are the inputs? In our case, we could go ahead and say they're real numbers. And if you plug a real number in and do something to it, then that output, any real number there, is going to give you a real number. And so this is a fancy way of saying, this is just a way of saying what the domain is and what the range is. If you had a 2 input function, let's say f of x and y, which comes out to maybe it's something like xy over the square root of 1 minus x minus y. Maybe it's something like that. The way we would write that is we would say, well, f, it takes 2 different real numbers. And it's not a vector. You'll notice xy here is not a vector. It's not taking a vector as an input. So they're 2 separate real numbers, and the way we would write that, the way we would show that here is we would say r cross r. So you're thinking, what does your input look like? It's 2 separate real numbers. So you take 2 separate real numbers, and the map, take any 2 real numbers, multiply them together, take any 2 real numbers and do that. What do you end up with?
Real.
Unless that might be a complex number. But yeah, okay, we'll say we could restrict it down to real numbers, whatever, right? Although it could be, it might even be better to say this here would be a map into the complexes. The outputs could be complex, right?
Yeah.
Plug in like a 5 and a 6. 1 minus that would be negative 10. Sure enough, you get a complex number there. Cool. So these are the types of functions that we've talked about before. This, the dot product, is a map. It's a function that takes in 2 vectors and gives you back a real number. And so we have a symbol for it. So instead of writing f, I'm going to write dot. And this is what mathematicians do. They say dot, that thing, just like f is that thing, dot is that thing. And where does it go from? Well, it takes, I'm going to do this in general first. The only thing about a vector space is that the underlying thing has to be a field. So let's say any field, I'm just going to go big blackboard bold F. That could stand for the reals, could stand for the rationals, could be complexes, whatever, who cares? And it could be any dimension. And I'll go ahead and do that. If you have any dimension of vector, A dot B, what you would do is you'd take the first entries and multiply them together. Then you'd take the second entries and you multiply them together. Then you take the third entries and the fourth entries and the fifth entry all the way down to the last entry, and you would just multiply them together. So this works in any dimensional space. That is what a dot product is. In our class, we're restricting to where the vectors are in R2, right? Real number in the plane. But in general, it doesn't have to be real numbers. It could be any field, and it could be any dimension. And so what it does is it takes 2 vectors of any dimension, and it gives you back an entry that's in the underlying field. So in our class, you have a question?
No, it's just...
Okay. So you see what's going on here, right? You have 2 inputs to a function. You show that those are the 2 types of inputs. Dot product could be any field, and in particular, it might make a bit more sense that in our class, this is what we're dealing with. R2 is the space of 2-dimensional vectors. If you are somebody in R2, you look like that. That is what it means to be in R2. Dot takes 2 of them, like an x and a y inputs, and it maps back to its underlying field, which in our case will always be a real number. And again, just here's another example. You could, for instance, have, say, 3-dimensional complex vectors, where like your vector u looks something like this, like 1 plus I, comma 2 minus 2I, comma 1/3 I. That would be a 3-dimensional, because you have 1, 2, 3. Complex, because the entries are all complex numbers. And what would that map to?
Complex.
The complex, but 1-dimensional, right? To its underlying scalar field, because it's a scalar product. I'm probably said this like 20 times now. I'll say it again. The dot product takes two vectors and its output is a scalar. Okay? Questions on this before we move on? So just one more time, in our class, the output of A dot B. A dot B itself. When you see that, you are looking at a real number. Right?
Yeah.
That is what, that right there, when you see that, that stands for some real number. Because that means do this and compute it, and then you get a real number. Okay? Everybody with me? Questions on that? Okay, let's drive the point home. Let's compute a dot product. Okay, so I'll give you two vectors. So again, inner product, you might be interested to learn if the inner product gives you a scalar, what do you think the outer product might give you? It's defined, it's the same setup, two vectors in some space.
A vector.
You might think so, and you'd be wrong. The outer product gives you a matrix. Oh, interesting. You won't see that forever. So, here we go. Here's an example. Let's let A be the vector -2, 3. And let's let B be the vector 3, 4. Let's compute A dot B. Now, just as an aside, I think today the way I've written everything out is I think for everything I'm going to do is I'm going to have this and then I'll write that. I could just have easily have not given them names, in which case I would have just written this dot this right here. Okay, you could do that. They don't need to have special names in order to do this. This means the same thing as that. Cool?
Yeah.
So, yeah. Ditto if it's in I and J. Right? IJ format. You could do it that way too. Okay, so what is this?
-6 plus 12.
Yeah, well, let's do it. It's that one times that one, so -2 times 3 plus that one times that one, which is 3 times 4, which you said is -6 plus 12, which I believe. And now what does that come out to?
6.
6. And so, again, you've taken the dot product of two vectors, and what you get is a real number. Okay? Question? It's really simple. It's really simple stuff. You're just multiplying component-wise, and then you just add them all up together. This, by the way, works for infinitely many dimensions. If your vector happens to have infinitely many entries, it still works. I'll let you think about that for a second. Okay, properties of the dot product. This is the stuff from page 606. I'm just going to write them on the board, and you're going to prove them. Property 1. A dot A is equal to the absolute value, the magnitude of A squared.
Oh.
Right? If that's A and that's A, you'd have A1 times A1, A1 squared. A2 times A2, A2 squared. What's the magnitude of A? The square root of all that?
Yeah.
So then you...
Yeah.
Yeah, right? Okay, yeah, proved. Well, you'll have to do that formally. Now, A dot B is indeed equal to B dot A. But we don't know that. We have to show that that's true. Here's one. Okay, A dot B plus C is equal to, can anybody take a guess what that might be?
A plus B dot C?
If this kind of acts, if we call this thing a product, think about this as kind of like a multiplication. What do you expect?
Oh, AB plus AC.
How about A dot B?
Yeah, A dot, yeah.
A dot B plus A dot C. And so help me. if you do something like this, you start there, and so you go A1, A2, dot, let's see, B plus C, and then you just go, oh, well, yeah, it distributes over. You don't know that it does. Like, that's what you're trying to prove. This is your next step, so you're like, yeah, and then you just dot them together. Oh, do you? Are you sure that this thing behaves that way? Don't get it. And this is what I mean by this is why this has to be proven, right? So the thing to do would first be to combine this into one vector, because we don't have a definition for the dot product involving 3 vectors. So you're going to have to first turn this into one vector and then dot those things together. So your next step would look something like this: B1 plus C1, B2 plus C2, and then you have your A1, A2, and then you dot that together. So it would be that times that plus that times that. And then you need to show that that's the same thing as that. Everybody got me on that?
Yeah.
And like, I didn't make it, like, I'm not at all disappointed that you guys did what you did, because I don't think, you've probably never seen anything like that before, where it's like, prove this property, and it's a property that's so, it's so, you're like, well, that's what numbers do, right? Yeah, but these aren't numbers, these are vectors, you know? And to really, like, throw salt in the wound, like, you're actually multiplying like m times something. You know, like you had like a m plus n times a vector. And it's like, well, yeah, it just distributes, right? Like, and so, no shame. No shame in missing those problems. All I'm saying. Okay? Okay, that's the third property. So we're not going to prove any of these. You're going to prove all of them. 4 is going to be m times a dot b is the same thing as, just right, yep, m times a dot b, and it's also the same thing as a dot m times b. So again, you just go use a definition that's a1, a2, that's b1, b2, do a bunch of manipulation, and make sure that you could turn one into the other. Let me make sure I haven't messed this up too badly. That looks all right. Okay. Okay, and now the last one. Ooh, and this, be careful with this. 0 dot a equals,
0?
or is it the 0 vector?
0 vector. Wait. No, because...
It can't be the 0 vector because the dot product is always a scalar. It's always a scalar. So careful on that, right? And if you just do it with this, like you do your A and then you just put 0, 0 there, it's pretty easy to see what's going to happen, but we still need to prove that. And you think, why do we need to prove that? Well, remember what we just did with the addition and subtraction of vectors? It's like, we don't know that you could just subtract from one side and then everybody's good. Like, you have to show that when you subtract, you get the 0 vector. And that any vector plus the 0 vector is that whatever vector you had. And then you could say, okay, then all the stuff we know about, you could subtract from both sides. Then all that stuff comes into play. But we don't know that ahead of time. It has to be shown. Okay, ready. Here's a definition. Definition. That's my shorthand for definition. Let theta be the smallest angle. I'm going to put in parentheses because I don't think your book says the smallest angle between two, this is very important, non-zero vectors Let's call them A and B. Now, what do I mean by that? So let's just think about any two vectors. And of course, from now on, for the rest of your life, you're going to think about a vector as coming out of the origin. So if I say two vectors, you're going to imagine, okay, there's two vectors sticking out of the origin. And so we're going to do that. And I wanted to keep that up here. Yeah, so I'm going to do this right. So we have any two vectors coming out of the origin. let's just say here's A. Because we're using A and B, yeah, A and B. So A and B. What do I mean by the smallest angle between the two? Well, there's two ways you can measure this angle. There's the obvious way, which is from here to here. We call that theta. The other way would be you measure around that way. Don't do that. We were talking about the smallest one. And so what that means then is you give me any two vectors in any space. I don't care, 3 space, 4 space, doesn't matter. Like, if they're both coming out of the origin. Then at the very smallest, this thing could be 0. Right? So in other words, what this here means is that theta, it could be 0. Right? If they're both pointing in the same direction, obviously. And if they're pointing in opposite directions, exactly opposite directions, then you get pi, or 180, right? But if you go any farther than that, right? So you're imagining, okay, here's some vector, and I have some other vector, and it gets to here, and then it's even bigger than 180. Well, that's not the angle you're measuring. You would just call it that one. That's the angle between. And so it doesn't, I don't even think your book goes into that. It's just one of those things that it's like the angle between them. Obviously, you're going to take the smaller of the angles. That's just what they do. So, okay. And just as an aside here, this is what we're about to do here is true in any dimension. And I just want to kind of show you this. Like, what we're about to do with this thing here that we're setting up. Because after this definition, we're going to derive something really cool. It's true in every possible dimension. And let me show you why. Here's 3-dimensional space. And let's say I have 2 vectors. And let's say, let's see how I want to do this. Let's put one back this way. So he lives here and he goes back a little bit. Say here, right there. Okay. So he lives there. That's terrible. Right, you see what's going on there?
Yeah.
He goes back a little ways. And let's do another one that maybe comes out, oh, I don't know, this way. And we'll say he lives here. Another vector. Everybody see that? So we have a vector coming out this way and another vector coming back this way. Well, check this out. I could take a plane and cut it through, you see what I'm saying? So that those 2 vectors are in the same plane. This one points, this one points back that way. This one points forward this way. Okay, they're in 3 space, yeah. Then I could just take them and orient them like this, flat.
Yeah.
Because what are you doing? Whenever you have a vector itself is a one-dimensional object. It's a line, right? Like, it's a line. That's a line. You have 2 lines. Any 2 lines, if they have a common point, you could just take them and just put them on the plane. So, in the same way, this would be theta. And it would still be true that theta at the most could be pi, and at the least could be 0. So what we're about to discuss will work for every possible vector, which is pretty cool. What we're about to do, at least I think, what we're about to do is really cool. But first we need a definition, and here's the definition. Let theta be the smallest angle between 2 non-zero vectors A and B. Then, it's 2 definitions. 1, A and B are parallel. That's the definition. That's what it is, parallel. What does parallel mean in terms of vectors? It means all of this. A and B are parallel if theta is equal to 0 or theta is equal to pi. Oops. That makes sense, right? Like, we have vector B, vector A. If A and B coincide, yeah, that's kind of what we think of as being parallel. If they go that way, that's also kind of what we think about as being parallel, right? So it's a pretty decent definition. And this is one. A and B are orthogonal if theta is equal to pi over 2. I don't know how many times last year I said orthogonal when I meant to say right angle. Like this is orthogonal to that, and it's at a right angle. It's perpendicular. Yeah. So this is a synonym for perpendicular, but it works in every possible dimension. Okay, so this definition here that we're talking about, this is a generalization of right angle, or a generalization of perpendicular. So in fact, that is what it means, perpendicular. It means the same thing. It's just now we've defined it in such a way that it will work in, like we just saw, 3 space, right? Like how could you have perpendicular in 3 space unless it's like, well, like this is how we could define all of that stuff. And so if it's pi over 2, it's a right angle, right? That's what orthogonal means. Okay? Okay. Okay, I'm going to get rid of this. So parallel, they're going in the same direction or exact opposite directions. And orthogonal, right angle. Okay? Now you might say, well, wait a second. If you have your B here and your A went all the way down to here, isn't it possible? Isn't that orthogonal too? And then wouldn't that be 3 pi over 2? And I'd say, what did I say about the smallest angle? That's not the one we're using that one. Right? Yeah. Okay. So, yeah. Okay. We're all on the same page. Orthogonal means right angle. Parallel means the other thing. Okay? So let's hold on to this. And this is about to get really cool. At least your math teacher thinks it's cool. So take that for what it's worth. Earlier today, here's the question. In terms of A and B, what's that vector?
In terms of A. A plus B. No. A minus B. Yeah.
Or is it B minus A?
B minus
Oh,
A.
it's B minus A.
Yeah.
The way I drew it is B minus A. And what we're about to do, that won't matter, as you'll see in a second. But that's the vector B minus A. Yeah?
Yeah.
Okay? Everybody with me? Let's just check that, right? It should be the case that if I add that to that, I get that. Yeah?
Yeah.
Right? Because that one plus that one gives me that one, which is that. And so A plus B minus A. A's are gone. I'm left with the B. Okay, good. I'm good to go. But now check this out. This is just a triangle, yeah? Okay. So let's forget about it being in some kind of plane. Or, well, being on some kind of coordinate axes. And let's just do this. What's the length of this one?
B.
How would I write that? How do I write the length of a vector? What do we call it?
The magnitude.
The magnitude. So that's the magnitude of B right there. And what's this one?
The magnitude of A.
The magnitude of A. And what's this one?
The magnitude of B minus A.
That's the magnitude of B minus A. So I'm going to do it this way. The magnitude of whatever B minus A is. Because remember, B minus A is a vector. Just like 7 minus 3 is a number. It's just I've written it that way just so that we know what we're talking about here. Okay? So those are just 3 distances. Those are 3 real numbers. Yeah? Positive real numbers. Everybody with me on that? Okay. Well, let's do this. I want to calculate a couple things. And in fact, why don't we go ahead, just to be sure here, we're going to pretend that A and B are just like these guys here, right? Because we're talking about it in the plane, although everything we talk about works no matter how many of these things we have. But it's still true. Let's just compute. I want these up on the board somewhere. What is that? How would I compute it given that thing? Like, what is it? If I said, find the magnitude of that.
The square root of
There you go.
1 squared plus a2 squared. Wait, no.
Of what?
a1 squared
Yep.
plus a2
a1
squared.
squared plus a2 squared. So if I squared both sides of that, what would I have?
The magnitude of a squared
Uh-huh.
equals a squared plus a squared. A1 squared plus a2 squared.
Okay, so everybody buy that.
Yeah.
Okay. Now here, I want this on here. What would that be?
b1 squared plus
Yeah,
b2.
right, okay. Okay, now here's the hard part. I want this guy. So, b minus a, the magnitude of. So, first off, let's find what b minus a is. So we have b1 comma b2, a1 comma a2 is equal to the magnitude of, well, that's just a vector. It's b1 minus a1 comma what minus what?
b2 minus a2.
b2 minus a2. And so that's what?
It's the square root.
The square root of
B minus a squared. B1 minus a1 squared.
there we go.
B2 minus a2 squared.
Everybody got that? Everybody believe that?
Yeah.
There's no funky stuff going on here. Now, it's just one thing. I'm just going to stop and do this. Had we done it the other way, where it was a minus b,
Oh.
the only thing that would have been different is that instead of b1 and a1, we would have had a1 minus b1. We would have had a2 minus b2. But then you square them, right? So you would have ended up with this a1 minus b1 squared plus
Which doesn't.
a2 minus b2 squared, which doesn't matter, right? Because when you square something, right, 3 minus 7 squared is exactly the same thing as 7 minus 3 squared, yeah? Because one's just the negative of the other, right? One's 4 squared and the other one's negative 4. I think it's 4. Yeah, squared. And so when you square it, it doesn't matter. And so this is one of those things I was saying before when I said, what's the length of that? Is it the same? Are the lengths the same? Yes. In fact, we can prove that the lengths are the same right here because that is equal to that. That is equal to that. Okay? Okay. So it doesn't matter whether we did it b minus a or if we did it the other one, a minus b. The point is we end up with this thing. Now I'm not really interested in that right now. I want to know what the square distance is. So if I square this distance, what do I get?
B minus a squared plus b. You just get rid of the square root.
Just get rid of the square root. So that's what I'm going to do. And I'm going to, just to save space, I'm going to do it right here. Okay. So b1a1 squared plus b2 2 squared. Okay, so we're going to need that here in just a second. Now, let's say I gave you a problem. And this was the setup. And I told you that the magnitude of A was, I don't know, 5. And the magnitude of B was, I don't know, 7. And the magnitude of B minus A was, I don't know, 3. And then I said, find theta. What would you do? You know 3 sides of the triangle. And you're trying to find one of the angles.
So you law of cosines.
Law of cosines. And so I'm looking, that's the angle I want right there. That's the side I want,
Oh, no.
right? So what we're going to end up with is this side squared, right? So
But don't you do the
we-
biggest side?
what?
You said to do the biggest side.
Well, that's not the question. Like but and this is general. How do you know that I didn't draw that way and I didn't draw that way?
Well, b minus a. B has to be bigger than a.
Yes, good job. But that's not what we're doing.
Yeah.
We're talking about, first off, any 2 vectors. That's the angle we care about.
Yeah.
And law of cosines works for everything because we're not trying to solve this triangle, by the way. If we were trying to solve that triangle, I might suggest a different way of doing it. But that's really not what we're going after right now. What we really care about is finding theta. That's all we care about. Since that's the case, we need the one of those cosines expressions that show where theta shows up. Because maybe this is, I don't know, maybe this is phi, and maybe this is, I don't know, xi, like, right? Okay, that's great, but right now we're talking about, and I got it out of here, we're talking about the angle between two vectors. That is the thing that we want to show up. So, what would that be? And so what is the law of cosines in this case?
C squared equals
Well,
that's
yeah,
good.
but in terms of these guys.
A vector A squared.
Yeah, so that's not vector A, that's the magnitude of A squared.
Plus the magnitude of B squared
Minus 2
minus 2 times magnitude A
There you
magnitude B.
There you go.
Cosine of theta.
Is what?
Cosine of theta.
Cosine of theta. That's the whole reason we did it. Because this is what we care about.
Yeah.
We don't care about the other ones. So yeah, if we were trying to solve the triangle and we had more information, I would say, yeah, go for the whichever one is the biggest first. One, we're not trying to solve the triangle, and two, we're doing this in general. So yeah, and if we did, and let's say we did another one first, we'd end up with some angle we don't care about. And then I'd say, okay, well now let's get to this one because this is the one we care about. But good question, right? Because you have that idea, like, well, wait a sec, like, and now it's like kind of becoming a rule in your head, like, I should probably go with the largest one first, you know. And so in this case, we don't care. So,
Yeah.
Okay. So we've done a lot of this work already. Let's just go ahead and replace, which ones do we want to replace? So let's do this one right here. Okay. So we have this thing squared is b1 minus a1 squared plus b2 minus a2 squared equals magnitude of a squared is a1 squared plus a2 squared. Magnitude of b is b1 squared plus b2 squared minus 2 times, and I'm just going to use a, and I'm just going to use magnitude b. You'll see why in a second. So, I'm looking at this and I'm thinking, okay, that doesn't, I mean, I could, if I were so inclined, subtract that over, divide by that to get cosine by itself, maybe.
And then
We
we're
should
done.
FOIL out.
But maybe I should, because maybe and I could see it right away. Like, well, if you square this, you're going to end up with a b1 squared. That'll be convenient. You'll end up with an a1 squared. That'll be convenient. And so let's just do that, right? So we have, just like you said, foiling it out. We get that minus 2 of this.
Yeah.
Plus that squared. Yeah? Check me on that. I don't want to mess this up.
Yeah.
Okay, now b2 squared minus 2a2b2 plus a2 squared equal to a1 squared plus a2 squared plus b1 squared plus b2 squared minus 2 magnitude a. I'm going to stop doing the little arrows because I'm sick of it. Okay, here we go. Just for right now. So now, okay, this is nice because now a bunch of stuff cancels. We get b1 squared, b1 squared. We get a1 squared, a1 squared. We get b2 squared, b2 squared, and a2 squared and a2 squared. All we're left with is minus 2 a1 b1 minus 2 a2 b2 is equal to minus 2 a b cosine theta.
Well, the 2's good.
We could cancel out all the 2's. There's another thing we could do. I mean, like, can we factor anything out of here?
The 2s, then the negative 2s.
How about the negative 2?
Uh-oh.
Yeah.
It's all good.
And so that leaves me with the a1, b1, and then what?
Plus
There you go.
2a.
a2, b2 is equal to negative 2. Oh, nice.
Oh.
Now here's the thing. From the very beginning of this, from when we talked about the definition of orthogonal and parallel, we said that A and B are non-zero vectors. Obviously, if you have a zero vector, Like, what are you even talking about? How could you measure an angle, right? So
Yeah.
no, you wouldn't have done this in the first place if one of your vectors happened to be the 0 vector. It doesn't make any sense. So obviously A and B are both non-zero, which means
We can divide by.
we could if we were so inclined. But I'm just saying, just something to notice. We'll do that in a second. But watch. So -2, -2 are gone. But what about, look at this. A1, B1, A2, B2. Is that anywhere else up there on the board?
Yeah.
But it's the dot product.
It's the dot product of A and B. So we could write this as A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. That is what the dot product is. It's a measure of how orthogonal these guys are. When they're orthogonal, what is the dot product?
Pi over 2.
Okay, so when they're
Yeah,
so when they're orthogonal, that angle is what?
Pi over 2.
Pi over 2.
Oh.
Plug in a pi over 2, and what do you get?
0. And so everything goes what?
When the so what you just told me. Hold up.
Right.
So what you just told me is that given
1.
what?
Wait, when you plug in pi over 2, you get a 0, yeah.
Yeah, because look at cosine,
Yeah.
right? Cosine starts up here,
Yeah.
goes down, and we don't care about anything past pi, right? So there's pi over 2. So what you just told me is that for given, of course, we're talking about given two vectors, A and B, both of them non-zero. Yes, okay, given all of that, what you just told me is this. If A and B are orthogonal, then the dot product is 0. A dot B equals 0. That's what you just told me, yes?
Yeah.
I said, what happens if theta is... Well, first of all, I said, what happens when they're orthogonal? And then you guys said, well, orthogonal means that theta is pi over 2. I said, yes. And then we plugged that in, and we said, okay, when that happens, you get cosine of pi over 2. Cosine of pi over 2 is 0. 0 times anything is 0. So therefore, A dot B is 0. On the other... Now here's the thing. We have an if-then statement. If Spot is a Dalmatian, then Spot is a dog. Can we conclude that if Spot is a dog, then Spot is a Dalmatian? No, but we could. But he might be. Spot might very well be a Dalmatian. So let's go. Let's check out this case and see what happens. Let's go with the other case. Let's go the other way. I'm going to assume if A dot B is 0, and now I'm going to try to show that they're orthogonal. So let's do that. I'm going to get all this work out of the way. Can I get all this work out of the way? Everybody saw how we got that? Because that's the important thing down there. Okay, there's all my work, and there's the result. That's the fruits of our labor right there. And it's going to be a good friend of ours. A great friend for the rest of your life. You will want, this is one of those that you'll want to memorize from this class. But anyway, now let's go the other way. Suppose that A dot B is equal to 0. Okay, so in other words, I could replace this side of the equation with 0. Yeah?
Yeah.
Everybody with me on that? Okay. And not only that, remember all of the preamble. That A and B are non-zero vectors, etc. The angle between them is between 0 and... Remember that? The angle between them has to be right in this range. Yeah?
Oh, yeah.
Right? Okay. So, if A dot B is equal to 0, then the magnitude of A times the magnitude of B times cosine theta, being the angle between them, is equal to 0. A and B are non-zero.
So we can divide.
You could divide by them. And so what do you get?
0 equals cosine of theta. So
And given that theta has to be in the range that it is,
Arc cos.
what does that mean? Okay, so arc cos, yes,
0.
which means that theta is equal to what?
pi over 2.
That's the only way of doing it, because we understand that any two vectors, you could always find the smallest angle between them is between 0 and pi. The only time that our friend cosine theta is 0 is when it's pi over 2. Therefore, if A dot B equals 0, then A and B are orthogonal. In other words, and this is big here, we have the implication going both ways. How do we say that?
Like arrows on both sides.
You could put it as arrows, the arrow going both ways. So instead of AB orthogonal implies this, or that implies this, then you do the arrow both ways. But another way that we say that is A dot B equals 0 if and only if
Oh, yeah.
A and B are orthogonal. So that means, right there, that if and only if means the implication goes both ways. That's what that means, okay? And whenever you have a statement like this, another way, the way to think about this is that these mean the same thing. They mean exactly the same thing. If one implies the other and the other implies the one, it's like it would be like saying if Spot is, or let's say if Patches is a Felis domesticus, then Patches is a house cat. If Patches is a house cat, then Patches is Felis domesticus. It means the same thing. So that's, Patches is a house cat if and only if Patches is a Felis domesticus, which means like it means the same thing. These mean the same thing. What does it mean for a dot product to be 0? It means that your vectors are orthogonal. What does it mean for your vectors to be orthogonal? It means that this is true. They mean the exact same thing. Saying one gives you the other. So in your homework, you say show that these two vectors are orthogonal. Well, if you could show that this is true, you got it. That's what you're trying to do, right? Questions? Okay. Here's another thing. Here's another nifty true. And I just want to stress, this is true in every dimension. No matter what, how many entries your vectors have, right? Your vectors might be sitting in a is it open? Just go on in. Oh, is it locked? I didn't know it was locked. Oh, weird. Hey, yeah, weird. I think Effie came through and she probably locked it in habit. Okay, so now check this out. If like I said at the beginning, if I told you to find theta, we got to this point. Now what do I need to do to get theta?
Divide by magnitude A.
Divide by the magnitudes. Can we divide by the magnitudes?
Yes.
Yeah.
Yeah, because that gives us a new formula here. A dot B divided by the magnitude of A times the magnitude of B is equal to cosine theta.
Take arc. Well.
And then you can take the arc cosine, but yeah, that's what you want to. If you commit this one to memory, then you're good, because that's not hard, right? You just divide and you're good to go. So let's find the angle between U and V, and here are U and V. So everybody got, actually, this is all pretty good stuff. So let's see. I'm gonna put that back up here. Okay, so the other one was that A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. That's your best friend. So, find angle between U and V. Here's U, and it's equal to root 3, comma 1. Here's V, and it's equal to 1, comma root 3.
Is there a 2 in there?
There might be a couple of them. Well, let's see. What do we need to do? What's the only thing we have up on the board that gives us theta almost by itself?
A times or A dot B
Right.
divided by
So
dot.
let's just write all that out. Let's say then cosine theta. Oh, there's theta, by the way. That's the angle between those two vectors. So cosine theta is equal to u dot v over magnitude of u times the magnitude of v. And let's just do this one bit at a time. What is u dot v? Something times something plus something times something.
U1 V1 plus U2
Which
V2.
is what?
Oh,
3 plus
1. No, root 3.
root 3 times 1, right? It's just those two multiplied together plus those two multiplied together, which is that. What's the magnitude of u?
A root of root 3. Root of 4.
Yeah, it should be root 4 because it's that squared, which is 3, plus 1 squared, which is 1. The other one is 1 squared, which is 1, root 3 squared, which is 3. So that's 2 root 3 over, that's root 4 times root 4,
So just 4.
which is 2 times, or 4, there you go, I was going to say 2 times 2, which is 4, which is root 3 over 2. So then, cosine theta. Now, cosine theta is between what and what?
And B.
Or I'm sorry, theta is between what and what? Yeah, it's between. Yes, theta is between those. Theta is between what two values? Must be at the smallest. It could
0
be
and
Pi.
in pi. So
Arccos.
okay,
It's
and then
it's
theta
just
gives you.
Pi over 6. Yeah.
I think so. Let's just see because I see a cosine and I see a root 3 and a 2. And so I'm going to do this, and I'm going to say, okay, there's that, and there's that. And I'm going to say, how do I get cosine out of one of these? Well, I would say that cosine pi over 6 is root 3 over 2. That's in the correct place. So root 3 over 2, that means theta is pi over 6. And look at what I did. I took this very same thing. That's the triangle I used to get this guy, right? Root 3, if he's root 3 in this direction
Yeah, it's just.
and 1 in this direction, that's the vector, which means that this is pi over 6. Now the other one, I just stood up this way.
Yeah.
He's still root 3 in the height direction,
Wait.
1 in this direction, yeah?
Yeah.
And so, wrong way, I
Yeah.
did it this way, sorry, there's that. I did 1 in that direction, root 3 in that direction, giving me that guy. And yeah, indeed, they both turned out to be 2 and 2, didn't they? Right? Both of those? Yes, of course they
Wait, what
did.
about theta of 90?
What?
Because what a cosine of the 90 degrees
What are you talking about?
also be root 3 over 2. That's the adjacent over.
Cosine of 90 degrees.
Well, in that.
The way we defined it, all that opposite, adjacent, blah, 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 was in a right triangle.
Oh, yes.
So when you're on this part of it, there is no opposite or adjacent. That breaks down.
Okay.
Remember, it was only opposite, adjacent, and all that stuff only worked when you're talking about in the first quadrant. And then we extended it beyond that.
Because
So
opposite over hypotenuse would just be hypotenuse over hypotenuse.
hypotenuse over hypotenuse, which doesn't make sense. And I mean, like, yeah. But then you don't have an opposite
Yeah.
in that case, right? And so that's different. That's different. So, okay. So, one second. What did I do? Okay, so then this is pi over 3, right? So in other words, from here to here is pi over 3. So in other words, theta is the same thing as pi over 3 minus pi over 6. Right?
Which is pi.
Right? Which, because, right, I went all the way up to pi over 3, brought it back until what was below it was pi over 6. I subtracted off pi over 6.
Yeah.
And what do I get?
Pi over 6.
Pi over 6, which indeed is what we got, okay? That looks good. Everybody get that?
Yeah.
That's how you're going to do this. The only thing that might be tricky is if it turns out to be a negative number. If a dot b turns out to be negative, then you have to think, well, wait a second. Like if it came out to be negative root 3 over 2, you'd say, well, hold on, cosine. There's pi over 2. Negative root 3 over 2 would be here in the second quadrant. And so it would be pi over 6, but in the second quadrant, so I guess it would have to be 5 pi over 6.
Yeah.
Right? Yeah.
Yeah.
And you could try that. You could do that. You could find a vector that's 5 pi over 6. And blah, 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 blah. Okay? Everybody good on that one? Okay, there's 3 more types of problems we're going to blow through. Because okay, like this. This is show that these vectors are orthogonal. I'm getting rid of all of this. That's been up there for long enough.
Shouldn't there be an infinity vector too?
You mean a vector that has infinitely many...
Like there's a 0 vector.
Oh, well, there should be a... Well...
Like with
You mean like so its entries are all infinity?
I
it
guess
has infinite magnitude and directly.
The problem is
So just
that,
array?
that the entries of a vector need to be numbers of a field. And infinity is not
Oh, yeah.
a number in a field.
It would be like a ray, only going in one direction. It's like a
Yeah,
line.
I mean, and there are things like that, but we don't call them vectors. So, but there are vectors with infinitely many entries. Those are certainly things. So we want to show that these two vectors are orthogonal. So here they are, 3 comma 6 and 4 comma negative 2. How can I show that they're orthogonal? What do I need to do to make that happen?
Show that
A
that
times
a times b
A
or a dot b
b
equals 0.
is 0.
So if I dot these together, so what you're telling me is if I dot these together and they come out to 0, then that's what it means to be orthogonal?
Yes.
Yeah.
Okay, so what is this? How do I compute this? What times what plus 1, what times what?
3 times
4.
6.
3 times what?
3 times 4 plus
Plus
6
6
times negative 2.
6 times negative 2. So that's 12
Yeah, that's 0.
minus
Minus
12 is 0. Am I done?
Yeah.
Yeah, I mean, here's the thing. As long as you remember the big theorem of today, that the dot product of two vectors is 0 if and only if the two vectors are orthogonal, then yeah, just remember. So you could even say something like, therefore, those little 3 little circles means therefore orthogonal. I mean, just whatever, just show it. Okay, now, here.
That's the symbol for.
The what now? Yeah, that's a shorthand for therefore. It's 3 little dots and a little triangle like that. So now here's another thing though. So so let's recall this. A dot B equal to A B cosine theta. Let's see what happens when, well, actually, yeah, I think we do want to do it this way. A dot B over A B cosine theta. Now, we've already shown that if they're orthogonal, then the angle between them is pi over 2, making this side 0, etc. What happens if they're parallel?
It would equal 1, right?
Right. So, well, what would equal 1?
Theta.
Theta
Or
equals what?
cosine theta would equal 1.
Yeah, and so in other words, so if A and B are parallel, then theta is equal to one of 2 things. What are the possibilities?
Pi
Or
0.
0, right? Meaning that the angle between them is either 0, meaning they're in the same direction, or it's pi, meaning they're in exact opposite directions. That's what it means to be parallel. So let's just see what happens. If it is parallel, then cosine of 0 is equal to what?
Pi. Wait. Cosine of pi over 2.
Cosine of... I plug 0 into cosine, and you're telling me
You
that
get
something
out
between
one.
1
You get
and
out
3
one.
pops out.
You get out 1.
You get out a 1. There we go. So, A dot B over A B equals 1, then we know that this is true. So if they're parallel, this will happen. And we could go play the opposite game, because it's an if and only if, right? Suppose that this is true. Well, that must mean that that's true. We know that theta is between 0 and pi. And so the only way for it to be 1 is when right?
Yeah.
You're saying, like, which theta is it true that this guy comes out to be a 1? Well, if you know that you're from here to here, the only possibility is that. Ditto if, what happens if, say, it were a negative 1? You'd say cosine of what equals negative 1 in this case? Pi. So in other words, depending on whether this is a plus or a minus 1, we'll tell, if it's a plus 1, they're parallel. If it's a minus 1, they're parallel. Does that make sense?
Yeah.
Okay. So real quick, I'm not going to go, there's a lot of calculations for this one. I'm going to just blow through it. I'm going to just blow through this real quick. And this says, show that the vectors are parallel and determine if it's the same or opposite direction. And this is what they give you. They give you A is equal to negative 5 halves I hat plus 6 j hat. B is equal to negative 10 I hat plus 24 j hat. And so A dot B, right? So we know what we're trying to do. We're trying to figure out if they're parallel. So let's go A dot B and then divide by their magnitudes, right? So we're going to go A dot B, divide by the magnitude of A, divide by the magnitude of B, and we get, and now I'm just going to, so that you could trust me on this, that it would take too long to just write out. This turns out to be 25 plus 144 on the top. Here on the bottom, this is the square root of 169 over 4 times the square root of 676. Yeah, which works out to 169 over 13 halves times 26, which is the same thing as 169 over 13 times 13, which is 169 over 169, which is 1. So, that is the same thing as cosine theta, where theta is the angle between those two vectors, which means that, is it parallel?
Yeah.
Yeah.
Yeah, that's the only way. So it is parallel. Is it in the same direction or the opposite direction?
Same.
Same.
Parallel and in same
If 1
direction.
minus 1 would be the opposite.
Now watch this. This is, you're gonna hate this. A is equal to minus 5 halves comma 6. B is equal to negative 10 comma 24. Watch what happens when I multiply this guy by 4.
Wait.
What's 4 times 6?
24.
4 divided by 2 is 2.
Yeah. So it's just
2 times negative 5 is...
so it's just a they're just multiple.
So, you could have just, they're multiples, and it's in the same direction, obviously. So, now here's the thing about smarter and not harder. Like, if you just notice that, and you say, wait a second. If I multiply this by a constant number and it gives me that, or if it were the other way around, right? If it were plus and minus like that, you say, wait a second, if I multiply this guy by negative 4, I get the same thing. That would be a much better way of figuring this out.
Yeah.
Right? But for the purposes of you getting used to using the dot product, please do this for your homework. Please do it the long way for your homework, because you do need to do this a bunch of times. And the more times you write this down or you write this down, the more it's going to get into your head. And so please do it that way. It will just benefit you. Okay? So just to get practice, do it the hard way. But just know that for the rest of your life, like after you get really comfortable with this, if you notice that, like for instance, if it's somebody gives you this 1 comma 2 and b equals 2 comma 4, they say, are these parallel or are they orthogonal? Are they in the same direction? You could just say, well, yeah, stretch that one by a factor of 2 and you get that one. So yeah, they're parallel, all right. Don't smarter, not harder, right? Yeah. But for the purposes of practice, do it the hard way for this homework. Everybody with me on that? Yeah. Again, the more, and it's good to see that. Yeah, okay, I could, and in every one of these, if it is indeed parallel, there will be a constant number that you can multiply one of them by to turn it into the other. That's what parallel vectors are, right? Like it doesn't matter what direction it's going. If it's going in this direction, there's v. If you multiply it by -3, it's going to look like that, and it's going to be parallel, right? You multiply it by +2, it's going to look like that, and it'll be parallel. And so, in other words, parallel vectors are always multiples of one another. And if you could easily see that, like I could not, when I did this one at home, I could not just easily look at it and go, oh yeah, -5 halves and 6, that's a multiple of -10 and 24. You don't see that right off the bat. But if it's obvious, smarter, not harder. But for the purposes of blah, blah, blah. Oh, that was, I didn't tell you what numbers these were. Yeah, whatever, you'll figure it out. And this is number 18 from the thing. And it's determine M. Determine M, and you'll see M's going to show up in the thing. Determine M such that, that's what my ST is, such that these two vectors are orthogonal. And they give you two vectors. Here are the two vectors they give you. 4m I hat plus j hat and 9m I hat minus 25 j hat. Right off the bat, I don't know about you, I like to have it in this form.
Me too.
I much prefer that, right? That's easier to work with for
Less
me.
letters.
Yeah, exactly. Though, and it wasn't until I took in linear algebra, or maybe it might have been a class afterwards, that I was like, oh, I could see why you might want to write it that way. And sometimes it is very nice. So it's not just, like I said, it took me years until I realized, oh, that is actually nifty in some cases. So it's not for nothing that they've introduced it. It's important. But now, if two vectors are orthogonal, then what does that mean?
The dot product equals 0.
The dot products equal to 0. So let's take the dot product. And this is the thing. We want the dot, if these are orthogonal, that's what they mean. Determine M. Find an M that makes this true. So let's do it. That's what is the dot product here?
36m.
36. So this times this is what?
36m squared.
36m squared.
A negative
minus 25.
Plus a negative 25 is minus 25 equals 0.
And then we just solve. Oh, but it's.
Add
Well, we
25.
can fact. Maybe?
Difference of squares. Add 25.
It is a difference of squares.
How about add 20? It is, but how about we just add 25? I mean, like, yeah. But yeah. So now.
Divide by 36.
There we go.
Take root.
There we go. What happens when I take that root?
Plus or minus.
Yeah, I get a plus or minus, whatever what.
5/6.
Do they both work?
Or, yeah, it would just be the other one, right? Because it's just negative, so it'd just be the other one.
Yeah, I guess.
Don't you have to-
I don't see why it wouldn't.
Then we have to plug M back in. And
I would check. That's what I would do. If I were doing this homework assignment, I would say, I better make sure here. And then take the positive one and plug it in. Actually do the dot product. And it should work. Both of them should work. So you should get 2 answers for this. Determine M such that it should be the case that M could either be plus 5/6 or M could be minus 5/6. There should be no problem with that. Because, I mean, what's going to happen? You're going to get this.
Yeah.
If it's both negative, then when you multiply the 2 negatives together, it'll be positive. Okay. You'll end up subtracting off 25. It should work out. So, yeah, and I think that's it. That's all I got for today. Any questions, you guys?